Hello guys, welcome to my YouTube channel. So today we are going to discuss one of the most important topics in bioprocess engineering, which is chemostat with a recycle. So first, before going into the design equations for chemostat with recycle, first let us see why chemostat with recycle is used and where can it be used. So the first thing that microbial reactions are autocatalytic. Autocatalytic means they process without on their own. So, and the rate of conversion increases with cell concentration. Of course, if the number of cells increases, the conversion rate also increases. More amount of product with the more increase in bacterial cell concentration. To keep the cell concentration higher than the normal steady state level, in a chemostat, cells in the effluent can be recycled back to the reactor. Okay, so what happens? On the right hand side, you can see there is a chemostat with recycle. So this is a chemostat, and from here, from the product, okay, so here you feed some initial concentration of bacterial cells, and from the product also some bacterial cells go out, and instead of letting go all the bacterial cells, you just what happens, recycle back some amount of bacterial cells back into the chemostat, so as a sort of inoculum. Okay, so what happens, why this is done? This is done mainly to maintain the cell concentration higher than the normal steady state level. Okay, so you recycle some of the product stream into the chemostat along with the feed stream. Okay, so what do? You recycle the product stream along with the feed stream. This is what recycling means. Okay, so this is done to maintain the cell concentration above the normal level. Now cell recycle increases. Why this cell recycling is done? Cell recycling increases the rate of conversion or productivity, and also increases the stability of some systems, such as in wastewater treatment, by minimizing the effects of process perturbation. Okay, so this is done mainly to increase the productivity. So if you have more number of cells, more conversion rate will occur. Suppose the cells is metabolizing some important metabolite or some secondary metabolites like antibiotics. You are producing some antibiotics, so the more the number of cells, the more the production of that antibiotic, so productivity will increase. And cells in the effluent stream are either centrifuged, okay, filtered, or settled in a conical tank for recycling. So this is very important. You cannot directly pass the effluent stream along with the feed stream in a recycle. What you have to do, you either have to do centrifugation or filtration or settling, and then you can send that stream for recycling. Okay, because why? Because the effluent stream may contain some toxic products which will harm the growth of other microbes present in the chemostat. So you first need to perform separation techniques, filtration techniques, okay, centrifugation techniques, and remove the unwanted substances from the effluent stream, and then you pass that filtered effluent stream into the feed stream, okay, for recycling. So now we come to the design equation. So on the right hand side, this is a chemostat with a recycle stream. So consider the chemostat system with cell recycle as depicted in this figure. If we do a material balance on cell concentration around the fermenter, so Fx naught. So if you remember our material balance equation, we write it as input minus output minus output plus of generation minus consumption. So this is our mass balance or mole balance. This is our mass balance or mole balance. So this is our accumulation rate. This is our original master equation for cell balance. So if you look at the right hand side, so suppose you have in the feed stream, okay, in the feed stream you have initial concentration of biomass which is x naught. Okay, in the feed stream you give a feed of flow rate F and containing initial biomass concentration which is x naught in the feed stream. So this will be your input. This is your input Fx naught, right? This is your input, and at the same time you are recycling certain fraction of the effluent stream. Okay, you are recycling also. That means this part is also your input. This part is also your input, right? So this is alpha F C x1. Alpha is the recycle ratio. Okay, C is the concentration factor or ratio of cell concentration in the cell recycle stream to the cell concentration in the reactor effluent. F is the feed flow rate, V is the volume of the reactor, x0 and x1 are the cell concentration in feed and recycled stream. So x1 is the this here, the x1 is what is coming out from the effluent stream. Okay, or x1 more specifically, x1 is what is coming out from the effluent stream and going into the feed flow stream via this recycle stream. So x1 is the cell concentration in the recycling stream. So this is the recycle stream cell concentration. Okay, so total biomass balance, if you do it, it is alpha F C x1. Now you can see this is also entering the chemostat. So this is also the input. This will also be the input. And here effluent what is leaving is x0 into 1 minus of alpha. So this is the cell biomass concentration in the effluent stream. Why? Because 1 plus alpha. So this is the recycle ratio. What is being passed into the recycle stream multiplied by the x0 initial biomass concentration will give you the biomass concentration in the effluent stream. And if you multiply it with the 1 plus fx1, 1 plus alpha into fx1. So what is this? This is actually the output. This is actually the output. Okay, 1 plus alpha together is a ratio, and you multiply it the feed flow rate, and x1 is the biomass concentration in the output stream, plus V mu net x1 plus V mu net x1. So this is the generation. This is the generation is equal to this is the accumulation. Okay. Now here we are considering no consumption, so consumption is 0. And now let us see the units. So we know for Bol balance, so final unit should be in moles per time or moles per second, for example. So here Fx naught. So what is the unit of F? Unit of F is liter per second, right? And multiplied by the x naught, it is x naught unit is in grams per liter. So it is in grams per second, right? So here moles per second, or we can do grams per second. Mass balance, for example, if we are doing mass balance, it is in grams per second. So L by S, this is grams per second. Now here also let us check the unit. Alpha is a ratio, so it has no unit. Feed flow rate is liters per second. C is the concentration factor, or this is also a ratio, so it will have no unit. X1 will again have unit of grams per liter, so it will be grams per second. Okay, so likewise you can check all the units of all these terms, it will have the same units of grams per second. Okay, so this is actually what they are doing. They are doing mass balance. Okay, mass balance, and it is mass per unit time. So final unit should be mass per unit time. Now at steady state we can set dx1 dt to be 0. So we come to the first expression here. So what we are doing, we are setting this term as steady state. There will be no accumulation. So whatever is coming is equal to whatever is leaving. So this term can be set to 0. So right hand side becomes 0. And if we solve this, okay, if we solve this, so and another important assumption is x0 is equal to 0. So it is a sterile feed, nothing. So the feed that is coming, it contains no initial concentration of microbial cells. So these are very important. These are very two important assumptions that we take. One is the steady state assumption and another is the feed, sterile feed. So if we do this and solve the previous equation, we get something of this type. So mu net is equal to 1 plus alpha minus alpha c into d. So d is actually what? Dilution rate is written as F by V. D is actually what? F by V. Okay. So while solving, you will get some terms which will have F by V form, and there you can, instead of F by V, you can write it as D. So dilution rate. So mu net is equal to 1 plus alpha minus alpha c whole multiplied by D, or 1 plus alpha into 1 minus c whole multiplied by D. Now since c is greater than 1, why? C is what? If you remember, if you go back to the previous slide, C is the concentration factor or the ratio of cell concentration in the cell recycle stream to the cell concentration in the reactor effluent. So this is the reactor effluent and this is the recycle stream. This is the recycle stream. Okay, this is the recycle stream RS, and this is the reactor effluent stream. This is the effluent stream. So C is actually a ratio of this recycle stream to the effluent stream. Now C has to be greater than 1. For performing recycling, C has to be greater than 1. Otherwise, you can't perform the recycle stream. That is, you cannot recycle the stream back into the chemostat. For that, you need to have this ratio greater than 1. That means the reactor stream. So the percent, that means proportion of this recycled stream should be higher than that of the effluent stream. Whatever is effluent stream should be lower. Okay, effluent stream part should be lower and recycled stream part should be higher. Then only your C or concentration factor will increase, and for performing proper recycling, your C should be greater than 1, and alpha into 1 minus C should be less than 0, because alpha is a ratio, and if C is greater than 1, if C is greater than 1, then obviously 1 minus C will be less than 0, negative term. Okay, then mu net is less than mu D. So this is very important. So net specific growth rate becomes less than the dilution rate. That is, a chemostat can be operated at dilution rates higher than the specific growth rate when cell recycle is used. This is very important, because if you go to my previous lectures on chemostat, you will remember the fundamentals that the net specific growth rate should be less than the dilution rate, otherwise washout occurs. Okay. Now we perform material balance here. In the next subsequent slides, we will perform material balance for two things. First is biomass, and then we will do that same thing for substrate. So first we do for biomass. Okay, so for we did for biomass. So this is for substrate. This is for substrate. We are doing material balance. So if you remember, this material balance we did for biomass. This material balance we did for biomass, and this is for substrate. So here some substrate is entering with a feed flow rate of F and initial substrate concentration of S naught. So this is entering the chemostat. Okay, so this is the input. Same design equation, mass balance you are doing. So this is the input plus of alpha Fs. So this is what in the recycle stream it is. So this is also the input. Okay, minus V mu g x1 by y xs. So this is what? This is consumption. This is consumption of substrate minus 1 plus alpha Fs. This is the output. Okay, here we assume that there is no accumulation of substrate is equal to V ds dt. So this is the accumulation. Sorry, here we assume there is no generation of substrate. Okay, so no generation. So remember, in case of biomass, in case of while doing mass balance for biomass, we assume there is no consumption of biomass. Here we are assuming there is no generation of substrate. Okay, so now again we assume another important thing at steady state, ds dt should be 0. So this side should be 0. So x1 gives us this form d by mu g y-axis s naught minus s. So d is the dilution rate, mu g is the growth rate, specific growth rate, y-axis is the yield coefficient of biomass with respect to substrate, s naught minus s. S naught is the initial substrate concentration in the feed stream, s is the what is there in the recycle stream. And how we are getting this I have explained in my lecture on fed batch. So you go and see how we are getting this term. So now we substitute that mu net expression here. So we substitute this expression in this. How are we substituting? That is the main question. So we know mu net is equal to mu g minus kd. So mu g is the specific growth rate minus the death constant will give you the net specific growth rate. Here we are assuming that the death constant is 0. So everything is getting formed, nothing is getting dead. So mu net becomes mu g. So in place of mu g, we can substitute this expression. Okay, so if we substitute this expression, we get x1 y-axis s naught minus s by 1 plus alpha minus alpha c. Okay. Therefore the steady state cell concentration in a chemostat is increased, this is very important, by a factor of 1 by 1 plus alpha minus alpha c in cell recycle. So cell concentration is increased in a chemostat with recycle, obviously, because 1 plus alpha minus of alpha c, this is a very small term, right? This I have already talked about. See here, c is greater than 1 and 1 plus alpha minus alpha c. So this term is actually less than 0. So this is a very small term. So if you divide something with a very small quantity, the resultant value increases. Okay. So again for substrate we have this mu net expression, and we know the monod equation. Monod equation is what? Mu net specific growth rate is equal to mu maximum specific growth rate mu m into s. This is mu net. We are assuming no death, so by ks plus s. Okay, so here if we substitute this expression, we get the expression for substrate. So this is the expression of substrate, and previously we got this expression. Okay, this expression from the previous slide for x1. x1 means the biomass concentration in the recycle stream. So if in place of this s, if we substitute this expression, we get this entire big expression for the biomass concentration in the recycle stream. So this is very important. So this gives you, suppose you are given the yield coefficient, you know the recycle ratio, you know the concentration factor, you know the initial substrate concentration, you know the value of Ks and the maximum specific growth rate, then actually you can tell what will be the biomass concentration in the effluent stream. Okay, so this is actually very important because it relates x1 with many important parameters. One is the yield coefficient, one is the monod constant, okay, another is the maximum specific growth rate. Okay, but here we need to take care that we are assuming many things. One is we are assuming steady state. Okay, we are assuming steady state for both the biomass and the substrate. Another thing is we are assuming In case of biomass, there is no the consumption of biomass, and in case of substrate, there is no generation of substrate. Okay, and another thing that we are assuming that kd is 0. That means mu net is equal to mu g. Okay, this is very important. Kd is 0, so no death is happening inside the chemostat, which is not actually the case. Some death obviously happens. So under these conditions only we get this expression of x1. Okay, so in the subsequent lectures we will delve deep into other types of chemostat.